first person I want to introduce is Tamas Budavari from Johns Hopkins, who's going to show us something very different. He's going to show us about big data from the world of astrophysics and how that might well relate to big data in marketing and marketing research. So, Tamas?
Thank you very much. Welcome back. Welcome, everyone. Thank you so much for having me. It's great to be here. Every conference has people who are not quite from the same area where everybody else is. I might be that guy. I mean, I'm here to learn about market research, but maybe I'm here to tell you about things that we have been doing with big data and could be relevant, and hopefully is relevant. I think it is relevant to everybody who either has big data, and what you define big data is different for everybody, I know, or has customers who have big data, or maybe want to dream big and they want to have big data. It turns out we went through this whole path of understanding how to work with these large data sets in astronomy, and from stars to big data analytics. But when we arrived and built the techniques and the machines that can deal with this, then it turned out to be more applicable than what we thought it would be. How would you open this up to some new community, new people, is actually quite interesting, because very often people can't think what would it be to have 1,000 times more data than you currently have. People often think, okay, maybe if I have twice as much data, what can I do with that? Maybe if I have 3 times more data, what can I do with that? But having 1,000 times more data is just impossible. So it turns out when we go and explore our colleagues and friends who are having these issues and they tell us their dreams, then we realize that, in fact, big data is in everybody's life, and even though they don't think it's possible to do it, it is. For us, big data started in astronomy, but really it's everywhere. I don't have to dwell on this. I think you all understand that it's growing fast. It's growing with the power of the computers, essentially, thanks to Moore's law. But that also means that complex analyses will take longer and longer if you want to do them. So we need new techniques. We need approximate techniques. You won't be able to do precise things anymore. You will have to do approximate things that are going to be, hopefully, with bounds, good approximations of the results. Now, the interesting thing is that when you have lots of data, it's not just the sheer volume that matters, but then you have to think about the errors differently. Certain things you can beat down. Statistical errors will go away, but systematic errors don't go away. And I see this in every talk I've gone to so far today, that biases are big issues in surveys and market research in general. We have been doing these studies for quite some time and thinking about these subtleties that you can't calibrate out. There are certain things you can calibrate out from your data, certain things you cannot. Now, also, it's very interesting to think about the different kinds of analyses that people want to do with the data. And it's very often a confirmatory study. Somebody would say, I have a hypothesis that this is going to be like that. And then you go and test it. But more and more so, and this is how astronomy started out, science and big data science is data-driven, meaning that you don't start out with a hypothesis. So for example, in astronomy, we didn't discover supernovae saying, let's see if something explodes in the sky. It goes the other way around. You see the data, and then you understand much later what happens in there. But you keep it in mind, and if nothing else, you keep these things empirically in the back of your mind. So just to highlight the kind of things that we've been doing and what we built, in year 2000, we thought 10 terabytes were all of data. But then we built a database that's even bigger than that. So we built databases that are 35 terabytes in size and 100 terabytes in size, and thinking about bigger collections now. In our building where we work at the Institute of Data Intensive Engineering and Sciences, we have a 10 petabyte system downstairs. So we're not afraid of data if it comes to that. How to analyze this data on the fly, how to see the results on the fly, how to compress high dimensions to the screen so you can make sense of things and look at things in the eye and examine them in context. Where it started for us was the Sloan Digital Sky Survey. And you might have seen these, or at least the images that this produced. The Color of the Sky, a beautiful survey that changed astronomy. But more importantly, it changed science, because it moved everybody who did science in a direction where you couldn't by eye look at the data anymore. You had to rely on machines and tools that would extract information for you. The amazing thing is that this team of researchers at Hopkins could essentially address these problems over a period of 15 years or so, not by going for off-the-shelf solutions which didn't exist, but actually building things from scratch. So now we have solutions from hardware devices that can go at incredible speeds, all the way to sophisticated statistical tools that will extract the information for you. And most of it had to be built custom, because tools that you are familiar with, and I hear often here, would not be able to cope with that kind of data. So just to give you a number, a hint, what scale we are talking about, the machine, again, I mentioned, we have in the building, can crunch through data at an immense speed at 500 gigabytes a second. If you were to do this on your laptop or a single machine, it would take a day or so. A second, just a second of aggregate speed that we can go through. All right, so the challenges we had to deal with were typically just not having champagne budgets. Right? So building the system that has not only fast computers, but also the fast I/O was part of the biggest challenge, because supercomputers have been evolving and doing simulations very well. However, they were not built to handle data. So we had to invent essentially a machine that was doing this. Okay. The data scope is this machine, which, again, you don't have to look at the numbers. Its specialty is that very affordable, very fast. Anyone can have this, or a subset of it, and crunch through data really fast if you go with this design. Okay. Rolf, at the beginning of his talk, or throughout his talk in the morning, if you went to the keynote, talked about hacking. And I thought, nobody is talking about how they do the things, like how the sausage is made. Maybe I'm the only one doing this. So it's not a very uplifting task. However, I think this is critical and very important to go through. And I'm here to tell you that things that happen between data collection and the magic on the screen, storyline and the visualization, there's a lot of things happening. So I talked about the machines a little bit. The lowest point of my talk, if you like, is to tell you about the architecture, but it's critical because this is what makes it tick. You have to have a pipeline that guarantees to get data from the hard drive, that's the data resides, all the way to the computing units. And where you compute is also important at that scale. There are machines called the GPUs, the graphics processing units, that are the best machines today to compute in the sense of power efficiency. And you can run tens of thousands of threads in parallel on a single chip these days. Just absolutely amazing what you can do with this if you know how to program them. One thing that we had to solve very early on is how we combine data from different sources. And I think this is, again, something that everybody is facing today. You have Twitter feeds, social networks, and survey data, everything coming together. Combining data, turns out, is not as simple as collecting them on the same hard drive. So we had to develop proper statistical techniques to make these fuzzy combinations and understand what belongs. In the context of astronomy, it's important to understand galaxies or understand the the dynamic evolution of things that happen. But in market research or surveys, it's interesting so that people can be connected throughout different channels and understood their responses in this huge, high-dimensional space. Databases are key. This is where the data resides. At the simplest, they are just a byte storage. You give them a byte, they give you back the byte. But of course, the trick is to do it fast and guarantees that you will get back the bytes when you want them. Now, to make it fast, we had to develop new techniques that index these spaces, in particular high-dimensional spaces that are really hard to otherwise deal with. Parallelization, job partitioning, all those things that make something go fast. If your website is taking too long, if a user is waiting for more than a second, that might be just too long. These are the kind of techniques that one can use underneath to make things go faster. If you were to think about GIS type of things, localization of Twitter feeds or anything else, you will need to have spatial components to your systems, GIS solutions, they're called. We have something that works very fast, a new technique called the hierarchical triangle mesh, or HTM. And we can pull out things from a 500 million row database in microseconds. So these novel algorithms are essentially the key. And streaming and indexing helps you to get there. But what they actually do in the end is try to figure out the interesting bits and components that you have to look at. In particular, if you were to just use textbook statistics, you might end up with maps or views of the data that is just dominated by outliers and all over the place. Big data is not just about sheer volume, but because if you have lots of data, it's all about things that stick out and that are outliers. You have to have proper statistics and robust statistics to deal with that. We developed techniques to do it, as well as techniques to create maps that will construct and reconstruct the structure in the data in front of your eyes, just in a two-dimensional map. And I know these plots don't mean anything to you, but these are sharper images and better views of the universe that apply to any type of high-dimensional data sets, not just the ones that we currently look at. Okay. So the big question is, the tools and approaches that have been developed at Hopkins and at the Institute for Data Intensive Engineering and Sciences, how do they apply to you as market researchers and survey researchers? And the answer is that if you have large data sets, very directly. Because the word hack that refers to getting things done, essentially from data to the visualization, covers a lot of things. And whether you like it or not, it's not as simple as writing a little R script or writing a little Python code. With big data, the world changes, and the good news is that there is definitely a lot of help and expertise available to do that. So we are very interested in learning more about the challenges that you are facing and the opportunities that you might have. Thank you.
Thank you, Tamas. Anybody have any questions? Nobody has a question. Everybody understood this, so if I give you a test, you all will ace this. Tamas, is this stuff really ready for us here in marketing research?
Absolutely. So everything that I've told you, they are a single slide each topic, but there are years of research, and not just research, but products. So when I talk about indexing, when I talk about database technologies, these are things that have been deployed in all the astronomy databases around the world, the largest ones that there are, hundreds of terabytes of data in aggregates. And every time you go on one of these interesting astronomy websites with images, you click on them, then these routines run in the background. Now, to make it applicable to market research, it just needs a bit of customization to understand the nature of the data that you currently have and how these tools can be applied. But these are things that are generic and easy to apply.
Good. Anybody else with questions? Okay, if not, we're going to move on to our next speaker. Thank you, Thomas.
Thank you.